Good evening, and welcome to yet another event in our celebration of women in STEM. My name is Mary Ann Lacerte. I'm in the English department, and I am here to introduce Dr. Elinor Gates because I first met Elinor via phone over a year ago when I was looking for an astronomer at Lick Observatory who worked with adaptive optics, perhaps, to help me research for my novel and my characters who do much of that work. And lo and behold, I found Elinor Gates, who's been a wonderful, just a treasure to work with and a fantastic science advisor to me in my writing. Elinor herself has a PhD in physics from the University of New Mexico. And while there, and a little bit later, working with one of the Air Force labs, she fell into the right optics career at the right time and was actually hired by Lick Observatory as a support scientist and a research astronomer before she even completed her PhD because of her new hot field. Something interesting to know about Elinor, a couple of things. First of all, she has a great address, Mount Hamilton, kind of a cool address. She lives on Mount Hamilton, where the University of California's Lick Observatory is, with about 35 other people, perhaps?
About.
Latest count? Yeah. Okay. She also has an asteroid named after her for work that she did at the Minor Planetary Center.
Minor Planet Center, yes.
Thank you. Asteroid Elinor, or 2650 as it's numbered. And last but not least, she finds time to sing in operas. So without further ado, I'll bring up Dr. Elinor Gates.
Thank you, Mary Ann, for that lovely introduction. So today I'm going to tell you a little bit about some of the new hot technology that's being used in astronomy to give us better views of the sky. And one of the things is that we're all used to looking up to the sky, and I'm sure we have all heard the little song, Twinkle, Twinkle, Little Star, and we've all had those romantic evenings with our loved ones looking up at the beautiful sky and looking at those twinkling stars. The problem is, twinkling stars, not so good for astronomers. What happens with the twinkling stars is that they're twinkling because the atmosphere is moving around, and that blurs our images. So we can use a technology called adaptive optics to clean it up and give us nice, sharp, crystal clear images of the sky. And I'm going to describe to you a little bit about how we do that with the technology and some of the exciting discoveries we've made using this technology, and also where we're going to go from here and how we can do even better in the future. Hello, move forward. There we go. Oh, too far. I've been struggling with PowerPoints all day. So this is Lick Observatory. This is where I work and live, as Mary Ann said. It is a large research observatory located in the San Francisco Bay Area of California. We have 8 active research telescopes. We have a 9th on the way, should be at the observatory delivered in the next about 3 weeks. We're very excited. We have a new telescope coming, a new toy to play with. But this telescope is the main one I'll be talking about from Lick Observatory. This is the 3-meter Shane telescope. It's our biggest research instrument on top of Mount Hamilton. And this is the one that we actually have the adaptive optics technology on and are using for science. I also want to stop at this point and note that the year of 2009 is the International Year of Astronomy. And so that this year was chosen to be the International Year of Astronomy because it is the 400th anniversary of Galileo's using a telescope for the first time to view the heavens. And Galileo discovered the 4 biggest moons of Jupiter, named the Galilean satellites. It's also, this year is the 50th anniversary of the Shane 3-meter telescope on Mount Hamilton. And another tie-in to Galileo and Lick Observatory is that our historic telescope in this other big dome here is the 36-inch refracting telescope, first large telescope on Mount Hamilton. When it was constructed, was the biggest telescope in the world. A fellow named E.E. Barnard actually discovered the 5th moon of Jupiter, Amalthea, using that telescope. So we have another Galileo connection there. And since then, all the other moons of Jupiter have been discovered with satellites and big telescopes photographically, not using an eyeball looking through a telescope, old school. But this year, being the International Year of Astronomy, there are lots of star parties and events going on. So, keep your eye out for exciting things to do and looking at the sky. So anyway, back to the main point of the talk, which is trying to observe stars from ground-based telescopes, which is most telescopes in the world are ground-based telescopes that astronomers use. And my colleague, Rem Stone at the Lick Observatory, has this wonderful quote: "Observing stars through the Earth's atmosphere is like bird watching from the bottom of a swimming pool. You wouldn't want to do it if you had a choice, because it's kind of hard to tell what you're looking at." Now, this is a bird. I've simulated what it would look like if you're trying to watch it from the bottom of a swimming pool. You can see it's a little hard to tell what it is. You'd be hard-pressed to tell what kind of bird it is. Now, I know because I took the bird picture, but any of you would be hard to guess because it's all distorted and it's hard to see the details. Now, astronomers looking through the Earth's atmosphere have the same problem. Our images are blurred. We can't see the details as well as we would like. And so it makes it harder to tell what we're looking at. So why do stars twinkle? Well, Robert Hooke suggested that stars twinkle because small moving regions of the atmosphere having different refracting powers which act like lenses. And this was back in 1665. He was a smart guy. He had it right. And so we find that little bits of air have different temperatures. They bend the light in slightly different ways. And then you have the wind, of course, moving that air along. And so not only is it light being bended, it's also moving. And so your turbulence is changing constantly. Isaac Newton also suggested with his telescope observations that the air through which we look is in perpetual tremor. The only remedy is a most serene and quiet air, such as may perhaps be found on the top of the highest mountains above the grosser clouds. Well, Newton was a smart guy too. He also had it right. In fact, Lick Observatory was the first year-round accessible mountaintop observatory in the world, because by the mid-1880s, when they started thinking about Lick Observatory, they knew that the best place to have an observatory was on top of mountains. Before then, observatories were close to universities. Universities tend to be in cities. Cities had lots of light, coal-burning stoves, gas lamps, such things. They discovered that that wasn't really the best place to have an astronomical observatory. So on top of a mountaintop, definitely better. And then an astronomer named Horace Babcock, who sadly passed away just a few years ago, he proposed actually correcting for the turbulence by using a wavefront sensor to measure the turbulence, and I'll talk about wavefront sensors a little bit more later. So just keep your brain on that term. And then using a deformable optical element to correct for that turbulence in real time, so that you're actually mechanically correcting this. And it's only in about the past 15 years that this technology has become mature enough that we could actually do what Horace Babcock suggested in the 1950s. So turbulence in the atmosphere does limit our view of the universe. Say you're looking at a star, you've got the Earth's atmosphere, it's turbulent, that's these little red wavy lines. At the end of the telescope, instead of having a nice pinpoint of a bright star, you get up with a fuzzy blob. And this turbulence is why the stars twinkle. It keeps sending the light in different directions, and sometimes your eye sees it, sometimes it doesn't, in varying amounts. More important for astronomy is that it spreads out into this ugly blob that doesn't tell you as much as you want. The consequence of this is that even the biggest telescopes in the world, and one of the advantages of a big telescope is that the bigger the telescope, the finer details you can see. But we're looking through the Earth's atmosphere, which blurs everything out. So the even biggest telescopes in the world don't see any more detail than an 8-inch backyard telescope you might be able to purchase for your own use at home. This is a real problem. We have two reasons we want big telescopes. One is to just collect more light. The more light we collect, the fainter the objects you can look at, potentially the more distance you can look at because you can see those faint distant objects. The other thing is to have the fine details. So we get 1 out of 2 from ground-based telescopes. We collect more light, but we don't get the added resolution. So where does this turbulence come from? So here I have a little schematic of a mountaintop with our telescope dome. One is that there are heat sources within the dome. You have electronic equipment generating heat. You have people generating heat. Believe it or not, each person in this room is generating about the same amount of heat as a 100-watt light bulb. And that all adds up. And that heat waves, if you've ever seen heat waves coming off pavement, goes up and blurs things if you try and look through that. Well, just imagine those same heat waves going out the slit of the telescope dome right in front of the telescope, blurring your images. Not a good thing. So we try to keep heat sources in domes down. We have wind blowing over the dome. Wind, of course, blows turbulence with it. So we get blurriness. There's what's called the boundary layer, which is sort of that 1 kilometer, 1 mile thick area of air between the ground and the upper atmosphere. And that, the ground has trees, buildings, other things, and that stirs up the air as the wind blows and causes even more turbulence. And then, there's turbulence in the atmosphere, and then up at the tropopause, there's another big layer of turbulence. That's sort of where the airplanes fly and the jet stream, and you have maybe different layers of air going different directions, and that stirs up even more problems. So we got all sorts of problems at all sorts of places. Stuff close to the ground we can try and mitigate. Stuff high up in the atmosphere, there's not much we can do about it. So this is what stars look like when you look through a small telescope. And these images were taken with the 40-inch telescope at Lick Observatory. So this is a typical, all the way at the far end there, is a typical image of a star, big fuzzy blob. If you look at light in just a couple milliseconds, that's the middle image. You'll see lots of speckles, speckly. That's where different bits of light from the star have gone through different bits of the atmosphere and been focused in slightly different places. And if you look at that for a long time, they're constantly moving around and eventually blur out to make that big fuzzy blob in a long exposure photograph. Ideally, you want a nice tight little spot like this one all the way at the image closest to me. Now that image is sort of the ideal case. That's where all the light is focusing in one place in a nice tight spot. So that's what we want. The other end is what we typically get. And so if we were above the Earth's atmosphere, we'd get that all the time. So there are 3 ways to eliminate blurring from the Earth's atmosphere. 1, go above it. We do this routinely. We have like the Hubble Space Telescope, which though it has had its problems, works phenomenally well. It's a wonderful telescope, but it won't last forever. It does have a next generation called the James Webb Space Telescope, which we hope will be launched sometimes around 2013. But it's very, very expensive to build satellites, billions of dollars typically. So that's not practical to have lots of them up there because we can't afford it. The other thing is to use computer post-processing. So if you take lots and lots of little couple millisecond exposures, like that middle image in the previous slide, you can actually sum up all those little spots, add them all up, stack them on top of each other, and get a nice high-resolution image. It's great. It only works for bright stars because otherwise you can't get enough light from the fainter stars. It also takes a lot of computing power, and it's just tough to do. And the third option is to use this new technology called adaptive optics. And this way, what we do is we measure the blurring through the Earth's atmosphere, typically by looking at a bright star, because we know what a star would look like without turbulence and blurring from the Earth's atmosphere. So that up to about 1,000 times a second, we actually have a new system at Lick Observatory that up to 2,000 times a second, we actually measure the blurring from the Earth's atmosphere using a bright star. And then we calculate what the turbulence is and then send a signal to a deformable mirror, which is just a small mirror that has little pistons on the back to put equal but opposite turbulence on the mirror as what we measure in the sky. And you get these lovely images. The problem is you need a bright star as a reference source, and it needs to be pretty much in the same direction you're looking, otherwise you're measuring the wrong turbulence. And that causes its own problems. So let's compare space versus ground-based telescopes. So as I said, I mentioned the Hubble Space Telescope. It's 2.4 meters in diameter, 96 inches. I believe Shane Telescope is 3 meters in diameter, or 120 inches, 10 feet in diameter. The advantage of the Shane Telescope, it's bigger. Hubble Space Telescope is pretty much the biggest telescope you can put in space using the space shuttle. Anything bigger you have to launch in a separate rocket, and it means that you can't service it later. Shane Telescope, 3 meters in diameter, bigger. We can collect more light with the ground-based telescope. You can build enormous ground-based telescopes because you're not trying to get into space, and the bigger something is, the harder it is to get into space. So Hubble Space, so because the Shane Telescope is bigger, we collect more light, as I already said. We also can see finer structures. And you'll see I talk about resolution at 2.2 microns, and I used units called arcseconds. And you're probably going, 2.2 microns, 2 arcseconds, what's all that? 2.2 microns is a near-infrared color of light. It's the wavelength of the light. And near-infrared light is the light just red of what our eyes can see. Most adaptive optic systems are optimized to look at near-infrared light because it's easier to correct the turbulence in the near-infrared than the optical light that our eyes see, though we're working on technologies to make it work better in the optical. So the resolution is essentially how fine a detail you can see. And it will help if I try to define what 1 arcsecond is. Essentially, an arcsecond is sort of how big something appears. So I have a dime here. You put it close to your face, it appears pretty big compared to everything else. Hold it further away, looks smaller. Now, say you give your dime to your pal and have him walk about 1.5 miles away. The size of that dime across, how big it appears, is 1 arcsecond. So that's pretty small. So that's a really tiny detail. If you were standing 1.5 miles from a friend holding a dime up, you wouldn't be able to resolve that dime. You would barely see any details of your friend. So these are tiny, tiny little details. So the Hubble Space Telescope in the near infrared can see structures that are essentially 1/4 of an arcsecond across. So take that dime and think 1.5 miles away and 1/4 that size. Tiny thing. Shane 3-meter telescope can see something that's about 1/5 of an arcsecond. So it can see tinier details. And so with adaptive optics, we can actually see smaller structures than the Hubble Space Telescope, which is really exciting because the Hubble sees great details, but we want to see even more. Now this gets even better if you go to bigger telescopes. So the adaptive optics system we built at Lick Observatory, we essentially built one for the Keck Observatory in Hawaii using the same technologies. And the Keck telescope is the largest optical telescope in the world. It's 10 meters in diameter. And so its details, it can see something that's about 1/20th of an arcsecond across. So even smaller details. The planned James Webb Space Telescope, which will be launched in something like 4 or 5 years from now, sees something that's about 1/16th of an arcsecond across. So you can see that a ground-based telescope today, using adaptive optics, will see things with more detail than the James Webb Space Telescope. So it's really, really exciting technology and way cheaper than putting a telescope in space. So how does an adaptive optics system actually work? Well, we have light coming from the star, coming through the telescope. And then after that, we have what's called a distorted wavefront. So I told you earlier, I used this term earlier, wavefront. But what a wavefront is essentially, think of all the light from a star emitted at the same time, all hits the top of the Earth's atmosphere at the same time, sort of in like a plane. It's nice and flat. But the turbulence of the atmosphere sort of makes things crumple up and wobbly. And it's this distorted wavelength that shows that light is going in slightly different directions. So when it focuses, you get a blob instead of a point. So here you have a distorted wavefront. It hits, oops, I think my batteries have died. Oh, there we go. You have this deformable mirror that has exactly equal but opposite turbulence on it. And then you end up with nice plain wavefronts again, these corrected wavefront in red. And then you have your high resolution camera there that takes your pretty picture, a high resolution picture. But some of the light actually gets diverted to the wavefront center, which is the gizmo that actually measures the turbulence. I won't go into the details of how that works because there are lots of different ways of doing it and they're all complicated and hard. But then there's a computer that takes what the wavefront sensor measures and sends the signal to the deformable mirror. So the deformable mirror, 1,000 times a second, is changing its shape to compensate for the turbulence. And it's a feedback loop. It just turns it on and it runs. Your typical deformable mirror, just talking about the technology itself, is sort of the cross section here. You have a thin sheet of glass, and thin glass is actually slightly flexible. Not very flexible, but slightly flexible. We put a reflective coating like aluminum or silver on the front side of that glass. On the back side of that glass, we glue little pistons, little actuators as we call them, that push and pull on the glass 1,000 times. Most of them are piezoelectric or PMN technology. There are some other technologies out there, but this is a pretty standard one. Actual deformable mirrors look like this. This is a mirror that you can see all the little actuators. We haven't put an aluminum coating on it yet, that one. So they look pretty much like standard mirrors. It's just the electronics behind them and driving them. They're changing shape just slightly. So what does an actual adaptive optics system look like and where does it go? Well, here's the Shane 3-meter telescope. And at the bottom of the telescope is the adaptive optics package. And that's where all the optics, the wavefront sensor and the deformable mirror, are all sitting there. So this all happens after the main telescope when we do this correction. Now this is our latest system. That's me, of course, in the picture to give it a sense of scale. Light comes down from the telescope at the top, bounces off lots of optics. One of the first things that hits is a tip-tilt mirror. That's like image stabilization. Most of you probably have video cameras that have little image stabilizers in them, so things are less shaky. Tip-tilt mirror in the AO system is doing a similar thing. It's just making sure everything stays centered. Light goes to the deformable mirror up here. You can see all the little wires coming out the back to drive those little pistons. Down here is the wavefront sensor. And then the big blue box is our near-infrared camera. And this camera is what takes the pretty pictures. So when an astronomer comes to Lick Observatory wanting to take data with the adaptive optics system, he's driving that camera and taking pictures. Or she, as the case may be. This is a little animation from the Gemini North telescope. It's an 8-meter telescope in Hawaii. And with luck, yes, the animation is starting. But this shows a schematic of sort of you're taking your large telescope, opening up the dome, pointed the telescope at a star, and then the star's light comes down through the telescope, back up, and then to the back, where we will cycle through to the adaptive optics instrument. And now we'll get a little cutaway view. So here's the light coming from the telescope, comes through, and then it bounces off the deformable mirror through this beam splitter that sends some light to the wavefront sensor and some light to your science camera. And in a moment, we'll see a nice jittery image, you know, every millisecond or a couple milliseconds it's taking a picture of the star. You can see how it's wobbling around and changing. Not very good. And then we'll soon see the distorted, wobbly wavefronts that are coming through the system. I like to call this the potato chip movie, as you can probably see why. And go through. So they're all wobbly, not being fixed. Now we turn the wavefront sensor on and start sending signals to the deformable mirror. And you can see it changing its shape. And then we'll see that the wobbly wavefronts now become nice flat tortillas, all corrected. The turbulence is gone. And soon we will see the image come over to the computer. And instead of a wobbly mass, we will have a nice stable point. So this is great. So this is an animation. This is in principle how it should work. So let me show you some actual data that we took from Lick Observatory using our adaptive optics system. And let's see if I can get this running. So you can see that this is every few milliseconds I'm taking exposure. And you can see on the far side there, it's wobbling around a lot. Can't really tell what's going on. Tip-tilt, things start staying stable, but still it's wobbly and changing. But then we turn on the full adaptive optics. You can see the top star, New Ursa Majoris, is a single star, no companions. Bottom one actually has a companion. And without the adaptive optics, you would have been very hard-pressed to know that there were two stars there. The separation of these two stars is about 0.4 arc seconds. That's pretty close together. And in fact, the nice thing about adaptive optics, I've been monitoring that bottom star, and I've actually been able to see its companion orbit around the main star. And so we're measuring the mass of these stars and doing that sort of research as well. But you can see the power of this technique. Without this, you would have never known the bottom star was two stars. Hello. Next slide, please. So with the Keck telescope, bigger cousin of the Lick Observatory 3-meter telescope, we're sort of looking at plots where over here, you can see what an image would look like without adaptive optics. A very low contrast fuzzy blob. With adaptive optics turned on, all of a sudden you can see all the flux is all squeezed into the center. You get a nice sharp image, really distinct. It's a factor of 10 almost improvement in resolution and detail that you can see. So with the Keck telescope, and this blows the doors off of anything the Hubble Space Telescope can image in terms of resolution. So we've shown this technique works, but we have a small problem, which is that you need a reference star. And it needs to be kind of bright, because you need to measure it 1,000 times a second to measure the turbulence. So that's fine. You have your bright reference star. You have your science target. Well, as your reference star gets further away, you're not looking at the same amount of the same turbulence. And so you're actually very limited. It turns out less than 1% of the sky is near enough to a bright star to use adaptive optics. Now, which is funny, you think of it, you see bright stars everywhere when you look up at the sky at night, but it turns out there aren't nearly enough of them. And bright stars to astronomers is way fainter than what our eyes can see. So this is a real problem. Luckily, we astronomers are clever, and if I'm clever enough to get the right next slide, there we go. We create a fake star using a laser. It turns out that we can use a laser and put a star wherever we want. And this is a picture of Lick Observatory using its sodium laser guide star. We were the first people in the world to use a sodium laser guide star for astronomy. The military beat us to it a little bit in the Air Force. They use lasers to illuminate satellites, to look at satellites with their telescopes using this technique. But we were the first people to do it in astronomical science. And so here we have a laser launch telescope bolted to the side of our Shane 3-meter telescope, and we shoot a laser up there. Now that laser is pretty powerful. That laser is about 20 watts in power. Now the little laser pointer I'm using here today, it's about 0.5 milliwatt. So we're talking many thousands of times more power in that laser beam than in this one in my hand. Now that causes certain logistical problems when we want to use the laser for this clever technique. One is airplanes, since we're just propagating it out there. And San Jose, or Lick Observatory tends to be near 3 very large airports. San Jose International Airport, San Francisco International Airport, and Oakland International Airports, as well as numerous smaller airports. So lots of airplanes in the sky. We don't want to hit an airplane with our laser. Now, if we hit an airplane, it's not going to blow up. We're not going to have flaming debris. But what we could have is blind a pilot. And in fact, it's illegal for any of you to ever point any laser at an airplane. Don't do it. Because even a small, low-power laser could dazzle a pilot and cause him to be temporarily blind. So we have a radar system on top of the telescope. Whoops, let me skip forward a slide here. We also have plane spotters. You'll see this poor person sitting outside, with a headset to talk to us, watching for airplanes coming close to our laser. So I work a lot with the FAA to make sure we don't hit airplanes. The other problem is satellites. Most of our laser light actually goes right through the Earth's atmosphere into space, which means if there's a civilization out there looking for laser pulses from another civilization, they might just see our laser. It's just barely powerful that they might see it. But our laser is an eye hazard as far away as the moon. So that our astronauts in space don't want to look down right at our laser. We could blind them, probably only temporarily, but that would be bad enough. We also have lots of sensitive downward-looking satellites, like spy satellites and weather satellites and other things, sensitive downward-looking cameras. So we don't want to blind those. We don't want to damage any satellites, and we don't want to cause an international incident by, say, blinding one of China's satellites. So there are all sorts of logistical issues, but it's fun because I get to talk to the people at US Space Command to let them know when I'm using my laser, and they will, the Space Battle Manager, that's its actual job title, will email me a list of, best job title ever, Space Battle Manager. But he'll email me back a list of when I have to shut down our laser to avoid illuminating an astronaut or a satellite. So how does this laser actually work to create a fake star? Come on, go back. There we go. So we got lucky with the sodium laser. It turns out that about 60 miles or 90 kilometers above our heads, there's a thin layer in our atmosphere where there are metals deposited, like sodium, potassium, calcium, a few others. And they're deposited there by meteors hitting the Earth's atmosphere. So every year with like the Perseid meteors and the Leonid meteors, they burn up in the atmosphere, they deposit more metals up there. They eventually drift out and react with things, so it's a good thing we have a fresh supply, constant supply. But we've chosen sodium, as is fairly abundant up there, to illuminate. So we tune the laser to just the right color of yellow light that sodium likes, and it absorbs that laser light. It goes, oh, I've got light, and then it says, oh, I can't hold on to it, and off it goes. And it re-emits the light, and so that we end up creating a fake star 90 kilometers or 60 miles above our heads. But this happens really fast. I mean, they absorb the light and release it in a fraction of a second, and so we constantly have to put more laser light up there to keep having laser photons come back and create the fake star. But it's really clever technique. The problem is nothing wants to laze at just that right technology, so it's really, really difficult laser technology to get this laser light of this color. But luckily, we at Lick Observatory and Lawrence Livermore Labs, who are really mostly to thank for our laser technology, got it working. So we showed at Lick Observatory using a laser works to create a star wherever you want it. So we installed a laser at Keck Observatory. This is Keck Observatory in Hawaii on top of Mauna Kea, biggest optical telescope in the world. We've actually now in the process of installing one on the other Keck telescope. There are two of them. Subaru telescope here, owned by the Japanese, like the technique so much, they've actually put a laser on their telescope as well. So at this point, most large telescopes, if they don't already have an adaptive optics system with a laser, are building one, because we've shown the technique works so effectively between Lick Observatory and Keck Observatory. So, and this is essentially what the laser beam looks like. Here's the main laser beam. That's just scattered light. We don't actually care about the main laser beam. We care about that spot up at the top. That's our fake star. So what's some of the science, the exciting science we have discovered with adaptive optics? Well, Franck Marchi is a researcher I collaborate with a lot at UC Berkeley, and he looks at asteroids. I don't think he has an asteroid named after him yet. He needs a friend to name one, because you're not allowed to name an asteroid after yourself. But he studies asteroids. And this is the asteroid Sylvia. And he discovered it has not one moon orbiting around it, but two. So Romulus and Remus are these two blobs off to the side. And he didn't use the Keck telescope for this particular observation, even though he could have. He actually was using the Very Large Telescope, which is owned by the Europeans. But he actually, once he discovered the moons, then he took lots of different exposures at different times to watch the moons go around Sylvia. And once you know how long it takes to go around Sylvia for these moons and everything, you can actually measure the mass of this asteroid. And then once you know the mass, you know the physical size, you can actually figure out its density. It's really hard to do, because we can't exactly go out to an asteroid, put it on a scale, and measure its mass. So this is really pretty cool. And so we're hoping to discover more asteroids with moons around them. And actually, Franck has discovered quite a few. Another thing is, asteroid-wise, is looking at the asteroid Vesta. And this is looking at the near-infrared light, and they just kept watching it. And you can see it rotates over about 20 minutes. And you can actually start seeing details and craters on its surface, which with a conventional telescope or even the Hubble Space Telescope, you wouldn't be able to see. So we're starting to learn about the surfaces of some asteroids without having to send a very expensive space probe out to get close to it, which we've done for some asteroids like Gaspra. Imke de Pater, also at UC Berkeley, she studies planets in our solar system. And she took these two images with the Keck telescope. Now, the image on the far side is Jupiter. You can see its great red spot, and below it, another little white spot. That's the red spot Junior. This picture looks like it was taken from a satellite, like one of the Galileo probes and such. But this was actually taken from the ground here on Earth with the Keck telescope. The yellowish colors are the tops of clouds reflecting sunlight. The bluish colors are the haze just below those clouds. But if you look in the thermal infrared, so look further into the red, beyond where our eyes can see, look at the great red spot and red spot Junior, you can see that you see almost nothing from the spots. The clouds are so thick in the great red spot. And the great red spot is about the size of 3 Earths across, give you a sense of scale. Junior is about 1 Earth across. But the clouds are so thick in these perpetual hurricanes on the surface of Jupiter that they block all the heat from the planet Jupiter below it. So they appear dark in these images. But these storms evolve. They change. Red spot Junior, I think has now dissipated. It no longer exists. It merged with the main spot, I think. But they evolve. You can't devote lots of time of a satellite that's trying to do all sorts of things to just look at Jupiter. It's much easier to take a ground-based telescope, because there are lots of them, and do lots of observations to track how these things are changing and evolving with time. So Io, one of my favorite objects in the solar system. Io is one of the 4 major moons of Jupiter, discovered by Galileo. Io is the only body in the solar system other than the Earth that has active volcanoes. And so we can look at the Keck telescope image here at the top, my right, your left. That shows, you can see all sorts of craters and features. If you look at from the upper right, the Galileo space probe, you can actually start matching up craters. From the distance we are from Jupiter, to actually see features the same from the Galileo space probe, which is right there at Jupiter, versus here is really amazing. And then you have, if you look at the long wavelengths, you see bright spots here in the lower left image. Those are active volcanoes, ones that are actually erupting, and they're hot, spewing hot material out. In fact, the surface of Io recovers large portions of it routinely with all its active volcanoes. And then the lower right blob is what Io looks like without any adaptive optics. So you can see the huge differences. And of course, one of the things we do at Lick Observatory is I monitor Io and looking for an active volcano. And then if I see a volcano erupting, then I contact other observatories so that they can look at it too, so we can get as much data as possible. So this is another picture of Io. You can see the Galileo space probe versus the same volcanoes here. You'll see on the Keck image that bright blob on the side. That's a volcano that just started erupting. So we caught it in the act. It's really fun to make those sorts of discoveries and figure out what actual is going on with the volcanoes there, because the volcanoes there spew lots of sulfur and stuff rather than the regular magma that our volcanoes here on Earth spew. So this is Titan, which is one of the large moons of Saturn, or the largest moon of Saturn. And this is some data that Antonin Boucher took. We were trying to take data on the same object at Lick Observatory, but we ended up in the clouds. So our collaborators at Palomar Observatory further south of us actually got the data we had been hoping for. But when we look at occultations, an occultation is when an object like Titan moves in front of a star. And Titan is actually weird because it actually has an atmosphere. It's a moon with an atmosphere. It's mostly methane, but we want to study the density and composition of that atmosphere. And part of studying density is you can actually see light from a star. If Titan moves in front of it, goes through Titan's atmosphere and gets bent by the atmosphere. And the amount of bending of the light and how much makes it through the atmosphere tells us things like information such as the density and temperature of the gas. So we knew that Titan was going to move in front of this one particular star. We turned on the adaptive optics and discovered, oh my gosh, it's not one star, it's two. Great, two for the price of one. So I'm going to start the first movie running here. At least I hope it will start running. And you will see Titan move in front of first one star, then the second. And if you look very carefully, you'll see it bright flickering around the edge of Titan as as it moves in front of it. And then the second one actually was great because it was just below the equator of Titan, goes the other way around the bottom of Titan. So you can see just faint little flickering. So we've been measuring those flickerings and how bright and faint they were. But it's hard because Titan is bright. So this next movie is when we subtract out Titan and look at just what the starlight is doing. And you'll notice it's really cool. At least I think so. You'll see the light from that go around the top. But if you look carefully, there's an image on the bottom of Titan. Now, if you look at the other one, you'll see bright spots along the bottom, but fainter ones along the top. So we got two measurements of Titan's atmosphere that we could measure. And it was great because not long after this, the Cassini probe actually sent the Huygens lander to, down through Titan's atmosphere to crash and get data on Titan. And it turned out that the data we measured this way matched what the satellite measured pretty well. So, which is great to have confirmation that this technique actually works and that without adaptive optics, we wouldn't have been able to do this. So Uranus, I'll go through just a few more pretty pictures. Uranus, one of the big planets in our solar system. Believe it or not, Uranus has a moon, has a ring around it. It's very faint, not very visible, not like Saturn, which has really obvious rings. If I change the contrast here, you'll actually be able to see the rings of Uranus. As well as we've got 3 moons here of Uranus. This was taken with the Lick 3-meter telescope. It turns out if you have an even more powerful telescope, like the Keck telescope, and Imke de Pater did this, not only does it have the main rings, but you have another ring, and this ring was a new ring discovered. They didn't actually discover it at Keck Observatory, but it can be seen with a ground-based telescope. Otherwise, it was only visible from the Hubble Space Telescope. Which is pretty impressive, because that is a faint, tiny thing to see. Neptune is also kind of neat. Without adaptive optics, you see some vague blobs. It has storms on its surface, much like Jupiter does. But with adaptive optics, you can start seeing details of the storms. We can track how they change with time, try and understand the thermodynamics and dynamics of the Neptune's atmosphere. And you can see in the near-infrared versus visible light, near-infrared, it shows up bright. Visible light, some of these dark patches. So we can actually, in multiple colors, figure out what is going on the surface of Neptune, we hope. So this is some research I've been involved with Marshall Perrin and James Graham. I won't go in a whole lot of detail on this because unfortunately I'm kind of running out of time and I've got a lot more to say. But these are Herbig AE/BE stars, which are youngish stars that still have gas and dust around them. And so we have bright stars in this Lick H alpha. There's a bright star there, there's another star there. We didn't know if this cloud of gas and dust going between them was physically associated with the two stars or if one star was further away and the other one in front. By using a technique called polarimetry, by looking at the polarized light from the dust. Dust actually preferentially scatters light to make it polarized. You can see that there's a star here and the little lines sort of circle around it. That means it's associated. The star is illuminating that dust. Up here, you'll see there's not so much. So that they're probably not really associated. We've done this for a number of objects. We've even modeled. We think there's a dark disk of dust in this one blocking some of the light. So we've modeled, sort of we have a disk tori and then stellar winds are blowing dust away out on the poles. I won't go into too much detail here, but it's really interesting stuff. And again, it's such tiny details. It's hard to tell without the adaptive optics technology. This is a planetary nebula. A planetary nebula is essentially the remnant of a sun-like star when it dies. Sun-like stars, when they get old, turn into red giants. Our sun will do this in about 5 billion years or so. So it's a good thing we won't be here when that happens because the Earth will probably end up inside the sun and be all hot and melty. But when the star gets, but when the star really dies, it tosses off its outer layers, and that creates a cloud of gas. And then the core collapses to a white dwarf. And the white dwarf is this point to the center, and then all this gas around it is what used to be the outer layers of the star. This particular object was discovered at Lick Observatory by W.W. Campbell in 1893. So it's been known about for a while, but they never saw the detail of all these, the bits of gas and such. So it's just a really pretty object. Globular clusters are huge balls of ancient stars in our galaxy. They could have hundreds of thousands, up to 1 million stars in them. We're looking at the very center of a globular cluster without adaptive optics. You see the bright stars, not much else. With adaptive optics turned on, all of a sudden, look at all these little stars in there. We can actually start looking at the population and understand how many stars are really in these clusters and how bright and how old they are. So there's a lot of things we don't know yet. This is image information by a colleague of mine named Andrea Ghez. She essentially is looking at the center of our galaxy. We think at the centers of all large galaxies, there are supermassive black holes. You don't see black holes because they suck in everything, including light. But if there's something around a black hole, you can see how the black hole affects it. And I'll talk a little bit more about that because that relates to my own personal research. But here we're looking at the center of the galaxy. Center of the galaxy is right there. We believe there's a black hole there. Not sure. But Andrea Ghez turned the Keck Observatory adaptive optics system to it. Whoops. I wanted the movie to run. I had problems with this one earlier today. Oh, there we go. You can see that where you previously saw no stars at all, you can see individual little stars. So what she's doing is looking at those individual stars. And you can see here another image using the laser, how we do even better with the laser than without it, using the same adaptive optics technique. But she's been tracking all those little stars and how they're actually orbiting the center of our galaxy. And with luck, this movie will run. No, maybe not. There we go. But this is a movie of all the stars and how they're orbiting around the center of our galaxy. So she has taken this information and actually measured the mass of the black hole at the center of our galaxy. And it weighs on the order of 1 million times the mass of our sun. So it's not, in terms of black holes at the centers of galaxies, it's kind of modest size. They can be up to 1 billion times the mass of our sun. But it's a pretty big black hole and not currently really sucking in anything. So at the centers of more distant galaxies, we have things called quasars. And this is my own personal scientific research. Quasars are essentially supermassive black holes at the centers of distant galaxies, not our own. And they're actively sucking in material. As material spirals into a black hole, it gets hot, it gets stretched out. You wouldn't want to get sucked into a black hole because your feet would end up there at the center of the black hole way before your head. You get stretched out like spaghetti. It wouldn't be fun. But as stuff gets sucked into the black hole, it gets hot. And so we can see that emission. We can't see the black hole itself, but we can see what it does to everything around it. Sometimes the stuff doesn't get sucked into the black hole. It sort of gets slingshotted off into these jets, going away from the center of the galaxy. So we see these jets sometimes, but mostly we see the emission from the accretion disk, as we call it, which is where most of the light is coming from in a quasar. It turns out that the light coming from the accretion disk can be so bright, it's brighter than the rest of the galaxy. So quasar is actually short for the name quasi-stellar object, because when these things were first discovered, they looked like stars. The galaxies were so far away and so faint, you couldn't see the galaxy. All you could see was that bright core where stuff was getting sucked into the black hole. So what I've been doing with my own research is looking at quasars and using adaptive optics so that I could shrink the quasar core down to a tiny size, and see fine details and see that small, faint galaxy around the quasar. And try and measure how massive that galaxy is. And it turns out there's a correlation between the mass of that galaxy and the mass of the central black hole. So this is one of my images. They're not as pretty as some of the images I've already shown you, because these galaxies are on the order of 6 to 8 billion light years away from us. So we're looking at truly tiny, truly distant objects. But this is one of the quasars. And the galaxy, you might see a faint little halo around it. That's the galaxy. It's only about an arc second across. So think of that dime being held by a guy, a mile and a half away. That's how big across this thing is on the sky. Tiny little details. So I'm able to measure the mass of that galaxy. We actually also discovered a companion galaxy down here. But the mass of this particular black hole is on the order of 30 million solar masses, I think. No, 300 million. Sorry, get the numbers right. Well, it's hard reading up there and getting the numbers right. But it's way more massive than the black hole in the center of our own galaxy. Here's another one, same thing. We have this galaxy. I've actually subtracted off the quasar core so I could see the galaxy a little better. This one actually had 2 companion galaxies. So as a regular basis, I'm discovering new galaxies out there. But this one has this particular galaxy has one of the biggest black holes ever discovered at about 1 billion times the mass of our sun. So it's truly enormous. And so I'm doing a census. I've looked at 30 or 40 quasars like this and measured the masses of them all. And eventually we'll try and figure out why most of them seem to be in large galaxies that have companions, but not all. So we're trying to figure out what all is going on there and the history of these over the history of the universe. So what are some of the new developments in the technology of adaptive optics now that I've given you a survey of some of the research done with adaptive optics? Well, there's different technologies we can use. Instead of a deformable mirror, we can use other things like MEMS devices, which are little electromechanical devices. They're based on silicon chip technology, and we all know silicon chips are pretty easy to make because we all have computers and cell phones, and even toasters these days have computer chips in them. But these are essentially tiny little deformable mirrors that we can use. So we shrunk the technology down and made it cheaper. We're actually applying these MEMS devices in an instrument at Lick Observatory called Villages. This is my colleague Bryant Grigsby, who I hired to help me with adaptive optics stuff. So we've taken that huge, you might remember the picture of me earlier with an optical bench with components that was like 6 feet long and 4 foot high. We've now shrunk all that using this MEMS technology to something that fits on a small tabletop. Adaptive optics not only is used in astronomy, you can also use it in vision science. You can use the same technology to look in someone's eyeball, image their retina, look at eye diseases and things like that. And with something that fits on a tabletop like this, you can reasonably start thinking in the future of maybe having something that clinicians can have in their office, as well as something that's easier to put on a telescope. And of course, these new technologies are also cheaper. The original adaptive optics system that we built at Lick Observatory probably cost on the order of $1 million. Not cheap. The system like this costs closer to the order of $100,000. So the price is coming way, way down. And eventually we hope to get it even cheaper so that every telescope in the world that wants to use the technology can do it. This is also a system that's being optimized so that we can look at optical light. All the pictures I've shown you this evening were pictures in the near infrared, light redder than our eyes can see. This will do optical pictures, so they'll look more like what you see out of, say, the Hubble Space Telescope. Pretty pictures. So where do we go from there? Well, super large telescopes. The bigger the telescope, the smaller the details you can see. Well, I'm part of a project to make a 30-meter telescope. So imagine a telescope 30 meters in diameter. That's over 100 feet. So let's say take a baseball diamond and steer that sucker around on the sky. So sort of mind-boggling. But to take advantage of a telescope that large, that's way too big to put in space. So you have to use adaptive optics to make it work effectively. You also have to use lots of lasers. One laser beam isn't enough. So the TMT telescope, this is the latest architect drawing. We hope to start building such a thing in, I don't know, 5 years or so, maybe sooner. But we'll have the laser guide star asterism generator. So we'll have a constellation of laser guide stars up there. So we'll have multiple lasers, multiple AO systems all working together so that you could get the maximum of a super huge telescope like this. And so this is the future of ground-based astronomy. And so, as I said earlier, any telescope that's big has an adaptive optics system, or will be building one in the very near future with a laser. So thank you.
Questions, because we're being videotaped for future use, I'd like to mic those questions. So Elinor will gladly take any, and you don't have to feel like you have to be a specialist in adaptive optics to ask questions. One of the reasons why I contacted Elinor is Lick Observatory in the University of California at Santa Cruz is very prominent with women astronomers and researchers, which is kind of an interesting spot to be. Questions? Ivana over here.
I'm always interested in the story behind the story, so I'm interested in what took you to the field of physics and to astronomy.
Even as a child, I was intrigued by the shows, say, Nova, that were talking about distant galaxies and black holes and all that stuff. And I think that stuck with me through my whole life. I was always good at math and sciences. And so it just seemed natural that I would continue it on and go into astronomy as a career. I was very lucky as a graduate student to fall into a research assistantship at the U.S. Air Force at Phillips Laboratory, where they were actually doing adaptive optics research. And it was the first time I actually really went into a lab playing with real hardware and equipment and said, wow, this is great. I really want to do this for a long time and make it better.
You were talking about when you created fake stars, like with a laser.
Mm-hmm.
I guess I was trying to understand like why you do that and what happens when you do it and how you are able, can study the stars surrounding it better by creating a fake star.
Yeah, well, we use the fake star to measure the turbulence in the atmosphere. So we're not really looking at it directly. And because it's in the optical light, it's yellow, and we're doing science in the near infrared, our pictures don't see the laser itself. But you have to have a reference source to measure what the turbulence is doing. Otherwise, you're taking a guess. And so we use the laser, goes up about 60 miles above our heads, excites sodium atoms up there, and then those sodium atoms de-excite, re-emitting the light back towards us to create that fake star. So whether you use a fake star or a regular star sort of amounts to the same thing. It's just that we don't have enough natural stars that are bright enough to make these measurements 1,000 or 2,000 times a second, that we have to create our fake star when we need one, because the turbulence is different in different directions. So you got to have a reference source in the same direction you're looking to measure the right turbulence and correct it properly. I hope I've answered your question. Okay.
I was just wondering why planets don't twinkle and stars do.
Planets can sometimes twinkle if the turbulence is really, really bad. and it happens like, as storm fronts move through. Mostly it's because stars are point sources. They're so tiny that even small amounts of turbulence send the light wobbling in different ways. A planet is big, so you've got light over here and light over there coming through the atmosphere. They might be seeing different turbulence, but on the whole, it's not as obvious that things are wobbling around. So while it is twinkling a tiny bit, usually our eyes can't detect it.
Eleanor, earlier today you mentioned how stars produce light and planets don't too. That might be kind of interesting.
Yeah, on a side note, I was asked earlier today what was the difference between planets and stars. And it's very fundamental in the physics. Stars actually generate their own light via fusion in their cores, nuclear fusion, and that generates the heat and the light that eventually makes it to the surface of the star and it glows. Planets don't have nuclear fusion going on in the core. They're too cold. They're not massive enough. And so that they could be gaseous bodies like Jupiter or rocky bodies like the Earth, but they aren't emitting their own light in the same, from nuclear fusion. And that's the main difference between planets and stars.
Out of the observatories that you talked about and showed pictures from, they were, like the Bay Area or Hawaii.
Yeah.
Places where like we here associate with like nice weather, that sort of thing. Is there a scientific reason for that? I guess it's a two-part question. Is there a scientific reason for that, and what are the chances of, say, a state like Michigan getting one of these like super high-end observatories, or is it just not in the cards for us?
I have to kind of admit that it's just not in the cards for Michigan. Big telescopes, modern telescopes, are very carefully sited. You want them on top of high mountains so that you get above most of the Earth's atmosphere, because the less atmosphere you have to look through, the less turbulence. You also want weather that's good most of the time. Dry sites that are next to large bodies of water tend to be the most stable and have the less turbulence. Because the less turbulence you have to correct, the better off you are. If there's lots of turbulence, it gets really hard to correct it. You can do some correcting, but it gets hard. So the best places in the world to put telescopes are places like Mauna Kea on the big island of Hawaii. Big, mostly dry mountaintop with just really smooth laminar airflow over it coming over the Pacific. And then it's like, this one quick little bump, and then it keeps going. The Andes Mountains in Chile are another excellent place to put it. Very high, very dry, and they just have winds coming from the Pacific over. Another good site is the Canary Islands. Off the coast of Africa, which is part of, I believe it's a Spanish territory. But they have relatively high mountains, but again, the air comes very smooth over the Atlantic Ocean before this little tiny bump where the telescopes are. So if you're going to invest tens of millions or hundreds of millions of dollars in a telescope, you want to make sure it's in the best possible place. Putting it in the middle of the Michigan, sorry, the cards, it's not the best place for it. You could put one here, and adaptive optics would certainly help, but it wouldn't be as spectacular as one of these world-class sites.
I have a question about Io.
Mm-hmm.
You mentioned the volcanism
Yes.
on that object, and you said that the Earth, of course, has volcanism as
Mm-hmm.
well, but is that a very rare occurrence in the universe, or is it
As far as we know, the only active volcanoes in the universe that we know of, it probably happens elsewhere, but we haven't discovered it yet, is Earth and Io have active volcanoes. Now, Mars has extinct volcanoes, so we know at one point there was volcanism there. And we're now starting to think that certain moons of Jupiter, like Europa, may have ice volcanoes, where you get sort of the slush erupting on the surface instead of hot magma. But yeah, volcanism is a very rare thing.
You mentioned all this cooperation with different countries.
Mm-hmm.
How much is that cooperation? Like, is it there? Is there any political pressure on your work at all?
Not for most astronomers. Astronomy, for the most part, is a very collegial science. There is competition. In adaptive optics, there are sort of two main groups that do adaptive optics. There's those of us here in the US, and there are competitors in Europe. We do have conferences, we exchange ideas, we do talk to each other, but we don't really work together. But there are many science teams that have researchers from many, many countries using many telescopes spread out to get the data they want. I mean, astronomers, we really want to learn about the universe and understand it and where it's going and where it's been. which is much more important than political considerations. Now things change a little bit when you're starting to talk money for actually paying for a telescope and building things. Then things get a lot more politically sensitive. But in terms of the science itself, there's not a lot of political pressure.
I was wondering if Keck was on, the Keck telescope was up on Haleakala, or is that some other?
No, Keck is on Mauna Kea.
Mauna Kea.
Yeah, Haleakala has a couple University of Hawaii telescopes, and the Air Force has a facility, the observing station there.
I've been there, so I didn't know what telescope.
Yeah.
Hi, you were talking about the fact that every galaxy has a black hole in the center, and that Earth's, or the Milky Way galaxies, isn't actively bringing anything in.
Right.
Yeah. What do you think the reason for that is? Is it because the galaxy is not as old as these other galaxies, or?
Well, no, actually, we think it's the other way around. We think it's because the galaxy is older. When a galaxy is young and the black hole is there, it's actively sucking in stuff and accreting and getting more massive with time. And we don't know, because we see many more quasars and active black holes the further back in time we look than we see today. But we think that maybe it sort of sweeps out its area and things become more gravitationally stable over time. That doesn't mean that it won't occasionally, something will won't get kicked into it and it'll be, for a short period more active. In fact, we do see that with the center of our galaxy and the black hole there. We do see the occasional flare up where we think some gas or some small star has gotten sucked in and we see a little bit of activity. So it's not just sitting there completely inactive. But one of the things that I'm trying to do in my research is actually figure out how active were they in the past and how massive they are and how the black holes grew and evolved, and at what stage they really stopped growing and sucking in material at the rates they did in the past. And so I'm surveying many, many quasars over a large span of time and distance to try and figure this out. But we just don't quite know the answer yet. But with techniques like this, we'll figure it out.
Are there other uses for adaptive optics outside of astronomy?
Yes. There are a couple uses that I've been involved with. One is laser communication. If you want to use a laser to talk from here to there, the turbulence just between here and there can really mess up the signal. You can use adaptive optics. There was a test being done between Lick Observatory and San Jose with a system to clean that up and make laser communications better. There are medical uses of adaptive optics. I've been involved with research of using adaptive optics to actually look inside your eyeball. And most of the time to diagnose eye diseases, the optometrist will look in there, doesn't get a very good view because your eye is moving a little bit. There's this vitreous humor inside your eye that has floaters and is moving around. Makes it really hard to see details of the retina. In fact, I actually have some images of some science. If I scroll forward here enough, we'll eventually see some retina pictures here. Yeah, here's what a old picture of adaptive optics to look at someone's eye. We've got your victim, or I should say grad student, sitting here. And then you have your researchers over here looking at their eyeball. So you can see details of the retina. And we've actually done studies looking at the cones in your eye, which are the cells that are color sensitive. And so we've looked at different people's eyes to see how many red, blue, and green cones there are. And you can see between a couple different people, we have very different proportions of eyes. Now, all these students had normal color vision. So these are things we're studying. You can also look at eye diseases, look at blood flow. I was the subject of an experiment where they wanted to look at blood flow through the capillaries in your eye. And so they were actually tracing each individual white and red blood cell going through the capillaries using adaptive optics and comparing that with, say, diabetic eyes where the blood flow isn't so good and diabetics suffer from a lot of eye diseases. Macular degeneration is another thing they've been studying. And with this, you have a non-invasive way of looking at seeing if medications are improving the state of the eye or if it's not making any difference or they're degrading. So there are lots of medical uses, particularly in vision science, for adaptive optics technology. So there's very exciting clinical uses for this technology in addition to astronomy.
Good evening. I was just wondering if you could share some of this statistics on what is happening in the job market in your area in light of what's going on in the economy nationally.
Ooh, I'm not sure I know a whole lot of the statistics. I do know that in general, astronomy is a very small field. There are on the order of, 5,000 or 6,000 professional astronomers in the world. So that we, if you get a PhD or a master's degree in astronomy, we can't guarantee you a job. But most people with a real interest in astronomy can find an astronomy-related job. It's been a little isolated from a lot of the economic woes right now. I don't know if that'll apply in the future as budgets get cut still more. Most astronomers are faculty members at universities, do some teaching and research. I'm an unusual astronomer in that I live and work at an observatory itself, so I don't do a lot of teaching, but I do work with the hardware and the equipment and visiting astronomers, showing them how to use our equipment to help them with their research. So, but I don't know on the whole how we're doing. But for highly educated scientists, job prospects are generally better than for someone that only has a college degree trying to teach in the humanities or get a job like that. So employment statistics for scientists in general are quite good.
Other questions?
I feel a little greedy asking 2 questions, but I noticed that you mentioned when you were talking about looking at the black holes, you talked about looking farther back in time.
Yes.
And I was wondering if you could explain what you meant by that, because we all know there's that connection between time and space, but when you say you're looking farther back in time, what does that mean?
Yes, that's a trickiness in that light travels at a finite speed. And so if something's very far away, it takes a long time for the light to travel to you. So while you're here, you're very close to me, it takes a tiny fraction of a second for the light to travel from you to me. When you go to the sun's 93 million miles away. It actually takes about, I think it's about 8 minutes for the light to travel from the sun to here. So we're actually not seeing the sun when we look at it as it is right now. We're seeing it as it was 8 minutes ago. It gets worse the further away it goes, you go. So I'm looking at galaxies that are on the order of 6 to 8 billion light years away. That means it's taken 6 to 8 billion years for the light to travel to us. If I look at something further away, that means it's taken more time for the light to get to us. So it means essentially the further away it is, I'm seeing it as it was further back in time. I can't see it right now. It may not even exist now. We don't know. And we'll know in 8 billion years when the light from now makes it to us. I hope that makes some sort of sense. But it is, I like to think of telescopes as sort of big time machines. We have no control over the time machine, really, and where we go. But it does only show us things as they were in the past, not as they are right now.
I'm going to go back to the black hole.
Okay.
I was just wondering if a black hole could ever suck in another black hole, and if you've seen that.
Yes, it could. Have we seen it? We don't know. They've built fancy detectors. I'm not involved in that particular research, called LIGO is one of the experiments that is actually looking for gravity waves, because black holes are dark. You can't see them. You can only see how they affect things around it. But if you got all that mass with 2 black holes, most stuff around it can't tell if there's 2 black holes or just one big one. But with gravity waves, as they spiral around and merge, that actually causes gravity waves, if gravity waves actually exist, which is not proven yet, far as I know. We'd see that. And so we would see it with that sort of equipment. But adaptive optics is not equipped to see that sort of thing.
Other questions? Okay, well, I'm going to ask one, or remind you of one. This afternoon you talked about the Milky Way galaxy and our nearest Andromeda galaxy and their movement. Could you talk about how those two are moving in gravity?
Yeah, that came about because someone knew that, wait a minute, everything in the universe is supposed to be spreading out because of the Big Bang, and all the galaxies we see are moving away from us, except for a couple exceptions, like the Andromeda galaxy, which is actually moving towards the Milky Way galaxy. And the Andromeda galaxy is part of our local group of galaxies. And in fact, the Milky Way and the Andromeda galaxies are the 2, by far, biggest galaxies in our local group. And it turns out the local gravity keeps our group of galaxies together, as opposed to more distant galaxies that are streaming away from us because of the Big Bang. But we are destined to collide with the Andromeda Galaxy in something like, I think, 2 billion years. I calculated at one point, but I can't remember what it was now. So it'll be a rather spectacular collision, except that most of the galaxies actually go right through each other, because most of galaxies is just empty space. But there is gas and stars, and they interact gravitationally. So interesting things will happen some couple billion years from now. Unfortunately, we won't get to see it, because I'm sure it would be a great light show.
Anybody else out there want the mic? Yes.
Maybe as a sort of a final question here, I know that Lick Observatory has a incredibly interesting history, and you were talking about the need to build observatories on mountaintops. Isn't it true that James Lick, who I think helped found the streetcars or the cable cars in San Francisco and was very rich, had to be convinced that the observatory was to be built up on a mountaintop far away from the downtown rather than right downtown San Francisco? Would you comment on him a little bit? Because he was quite an interesting character.
Yeah, James Lick was definitely an interesting character. He was a very wealthy businessman in the state of California at the time, one of, in fact, the wealthiest people in the United States at the time. In the 1860s, he had amassed a fortune of on the order of $3.5 million, and that's 1860s dollars. So he was fabulously wealthy. He wanted a monument to himself, and after many great ideas, like building a pyramid to himself, bigger than any in Egypt, luckily he didn't do that. George Davidson and George Madeira knew James Lick. George Davidson was the president of the California Academy of Sciences. George Madeira was an astronomer. We don't know which one of those two suggested a telescope as a monument for James Lick, but James Lick eventually agreed. And then it came to the astronomers to convince James Lick that, yeah, it didn't need to be in downtown San Francisco, that if he really wanted to have a lasting monument that would be truly phenomenal, it needed to be on top of a mountain. So they went searching for a mountaintop on which to put the telescope. Astronomers had figured out high mountaintop is where you want an observatory. James Lick owned a lot of land around Lake Tahoe in California, so they said, okay, let's use one of the mountains in the Sierra Nevada. But it was too snowy, too rough country. They couldn't reasonably put a telescope up there and have it be accessible all year round, because James Lick wanted his telescope to be used to the fullest ability possible. So they scrapped that idea. They then chose another mountain in the San Francisco Bay Area, up in the Napa wine country, called Mount St. Helena. James Lick at that point had a stroke. He wanted to see where his observatory would be. He couldn't ride a horse, so they put him in the back of a buckboard wagon and mule-drawn wagon. There was no road to the top of this mountain, so they sort of bushwhacked their way up the hill. At some point, they hit a rock, over went the wagon, out went James Lick. He said, that's it, we're not using this mountain, take me home. So that's what they did. So the astronomers started getting worried, where are we going to put this observatory? A geologist in the Bay Area, part of the California Academy of Sciences, Mount Hamilton, highest mountain in the Bay Area. That would be a great site to put a telescope. And the board of trust to build the observatory was worried, because they said, well, he wants to see his final resting place. It has no road. We'll have the same problem we had on Mount St. Helena. Luckily, James Lick could see Mount Hamilton. He'd been looking at it for years from his manor house in San Jose, or actually in Santa Clara, the neighboring town. And he said he didn't have to go up there. So that sort of is how the mountain was chosen. He is up there now. He never lived to see the construction of his observatory, which at the time was the biggest, best telescope in the world. He died in 1876, and he was interred in San Francisco. We disinterred him and put him at the base of the telescope in 1887. In 1888, they finished construction of the telescope on top of him. And so not only is that historic telescope, it was the biggest in the world at the time, it's also his tombstone.
Any other questions? Okay, I, of course, just have one more. When I was researching women in astronomy, especially, there were a couple of names that I came across. One of them, somebody that you have worked with directly at UC Santa Cruz, Dr. Sandra Moore Faber. Another one was Vera Rubin, the woman who's actually credited with discovering the concept of dark matter in the universe. And what I was surprised at, and we talked about this a little bit this afternoon, was that when Vera Rubin, around the 50s and 60s, was trying to do observations, she was not allowed as a woman to use the telescopes. Can you talk a little bit about being a woman and many of the, there's what I see as a predominance of women at UC Santa Cruz, but you also have neighboring facilities who don't necessarily have that many women.
Yeah, UC Santa Cruz and Lick Observatory, for whatever reasons, I don't actually know what they are, is a very woman-friendly environment. And I don't know whether it's because of prominent people like Sandy Faber there that people see as a role model and flock to her, or or because she's chairman of the department, it has more family-friendly or women-friendly policies, or they don't put up with any crap from guys doing inappropriate things. I don't know what it is. Historically, women have had a rough time in astronomy. Many observatories, I believe, I'm not 100% sure of this, but I believe Palomar Observatory in the 1960s did not allow women to observe. Lick Observatory never had that policy, but historically women weren't encouraged to be astronomers. They could take astronomy classes, they could be very good at mathematics, and so even Lick Observatory 100 years ago had the lady computers. The men would take all the data and the ladies would sit there during the daytime reducing it all, doing the mathematical calculations, but they wouldn't necessarily be using the telescopes directly. So they were doing astronomy, but they weren't astronomers. Things have changed a lot for the better, and of course they will continue to improve as more and more women get involved in the science and technology of astronomy.
Thank you.